Q&A, but I would ask you to please type your questions into the chat box that you'll see in the upper right-hand corner of your WebEx screen, and that just makes it easier to control, the order that we answer the questions so that everyone's just not talking over each other. So I'll read your questions, and Dr. Lay will give the answers. So Dr. Hanh-Phuc Lay is Assistant Professor of ECEE at the University of Colorado-Boulder. He received his BS degree from Hanoi University of Science and Technology in Vietnam in 2004, his MS from KAIST in Korea, and PhD from UC Berkeley in 2013, all in electrical engineering. From 2012, he co-founded and helped secure approximately $14 million in funding and served as the CTO at Lion Semiconductor until 2015. And since then, he's held several R&D positions at Oracle, Intel, Rambus, JDA Tech in Korea, and the Vietnam Academy of Science and Technology. His current research interests include miniaturized on-die power conversions, large conversion ratios, smart power delivery and control for high-performance IT systems, data centers, telecommunications, robots, automotive, mobile, wearable, and IoT applications. He received the 2012 to 2013 IEEE Solid State Circuit Society Pre-Doctoral Achievement Award and the 2013 Seven Rosen Funds Award for Innovation at UC Berkeley. He's authored 2 book chapters and over 40 journal and conference papers, and is an inventor with 16 U.S. patents. And with that, I'd like to open it up to Dr. Hanh-Phuc Lay.
Thank you very much, Rogelio, for the introduction, and thank you all for attending. So for this talk today, and the introduction was really comprehensive. So for the talk today, I will like to introduce you to the converters for large conversion ratios with high current density. So for this talk, this is actually a big part of that is supported by PowerAmerica. We started the effort a little bit earlier, but then we now really, together with PowerAmerica, we try to push it to a new limit in the converter performance. So I'd like to start off by, having a little bit on information on the group of focus that my group is working on, and then dive deeper into certain converters that we need for large conversion ratio for specific application in data centers and telecommunication systems. So a lot of people now these days talk about the network of everything, and by the network of everything, I'd like to, put them into different circles of related components. So the first related components are the components or the devices that are, essentially surrounding us in the room that we are in the building that we are in, or in home, that are computers, smartphones, smart cameras, and even, some smart cups. So all of these devices are essentially things surrounding us that we are very familiar with. And then the network of everything can be extended inside and outside. So by inside, what it means is that, well, all these devices are already going, like electronic devices are already going inside our body with the biomedical devices to help us understand more about our biological system. And expanding outside in terms of we have smart cars, we have electronic devices to understand more about our plants, so the network of things or Internet of Things, right? Understand more about our livestock's health and buildings and so on. And this certainly expands further into not just a city kind of level here, but beyond that, to the devices that are covering a lot bigger scale in terms of data center, in terms of drones, airplanes, robots, wind power, and solar power, and so on. So all of these devices or systems in this network of everything really have one common need, and that is how to power them. All of them have similar power needs in that they need the power to be compact, they need the power to be efficient in all of this. So my group, we can't claim at this point that we cover all of these devices, but we are going to, point out some of the devices, examples for each of these circles that we have experience on, and hopefully we'll put your belief towards that we can actually support other devices in the same circles and all of these circles as well. So the critical needs of interest for all of these devices are related to power. For example, in mobile devices, we need to extend battery lifetime. For implants and wireless sensor network, we need ubiquitous and have a different indefinite lifetime. So again, for power. Electric car, we want them to run more miles from one charge. For battery, we want to charge faster with less heat dissipation. For data center base station, we need better power delivery for lower loss and lower cost. Renewable energy, we need better grid integration, smart grid distribution. Robot and drones, we want them to fly longer, more efficient takeoff and landing. So all of these are related to power, but I want to dive specifically in one of the examples in power management in smartphones that tells a little bit about the story here, and actually the similar story can be told to many of these systems. In the phone, for example, in iPhone particularly, moving from iPhone 3GS to iPhone 5, iPhone 8, and now iPhone XS, we see a trend of the occupation of power management area is increasing from 10% of the board to 18 to 20 and to 30. So now, when we first look at this, we say, well, it is because the board is reducing, so that's why the power area is, increasing. But that is the key of the story, is that, well, it seems that everything else is scaling down, except for power management unit. So the space for the power management keeps increasing relatively. Maybe the absolute space is not increasing very much, but the ratio is increasing rapidly, and we need to do something about it as power system and power electronics design engineers. And the reason why it's increasing because the complexity of the systems that we need to support now keeps increasing fast. From the very simple circuits right here, maybe 5 or 6 outputs here, we increase to a large number of passives, and all the components with the dots here are all inductors. So you can count the number of inductors to find out how many switching converters that we need on the phone. And that number is just keep increasing with more inductors, more capacitor, and even more complicated later on for iPhone XS. And no Moore's law here to help with this power management for these passive devices. Now, I know the PowerAmerica is more interested in, even higher power, but a very similar story can be told here, and it is related to how we support the very complex and multiple output system that we need to support them, not just with one single output here, that can support all of them because each individual sub-block, or in this particular case, the cores within the processor actually needs different voltages to support them efficiently. So if we don't provide them individual voltage, then we are essentially wasting the power to them. So there's clear need to multiple independent power supplies and per block power management dynamic power supplies. But we can't do this from the off-chip components because if we do that, we saw the story earlier, the power management IC or the power management integration part can be reduced, but then the passive components is fundamentally not great when they are, and they need more integration here. And many off-chip components is undesirable, especially large off-chip components, especially like inductors. So this is a common problem in different systems, and we can look at the more interesting application to us in some of the PowerAmerica application is that the need for advanced power converter in data centers. So in data center, we have been talking about the structure that we support AC, high AC input, high AC voltage at the input, and then we go through AC-DC conversion and DC to AC conversion, and then we have the backplane power distribution network that have another AC to DC and DC to DC to make a 12-volt, and then at that time we have a point of load converter. So clearly we see that that structure goes through a lot of conversion stages here, and that's why we lose a lot in terms of losses. We are talking about, 73 billion kilowatt hour by 2020 in terms of power consumption for this, and for just data center in the U.S. alone. And 50% of that is really associated with the conversion stages and deliveries. So the newer structure that a lot of people have been talking about in the last few years, including Google and HP and other companies, Facebook as well, is that now if we need to deliver that power, we want to start from the AC-DC microgrid and then go to the 48-volt local distribution, and then we have a distributed battery here with a 48-volt right at the rack, right at the server rack. And then from that server rack, we have a 48, for each rack, we now have a 48-volt point-of-load converter that converts down the voltage from 48-volt burst to 0.5 to 5 volt total. And then from there, now we can actually selectively provide all the power, all the voltage rails that we need on the server rack, including the fiber that may need that can be used directly for the processor, for example, from Intel. So we want a very converter with large conversion ratio, but it should still be need to be compact for scaling, so that we can support different loads here at the server board. And if we talk about the challenge of this power management circuits, we are talking about higher power density here, that we need to provide a larger current at the output while consume a smaller space. Now, in the high power density, I really want to emphasize on a specific application in data center is that we actually need a low output voltage. So with high power density or high power at the output at low output voltage, we actually have extremely high current density, and that is actually a differentiator. That is actually the difficulty in the whole power delivery that we all know. So another thing is that we still need also the small component counts and area. We still need to support large conversion ratio so that we can reduce the current distribution at the input and reduce the number of conversion stages that we talked about earlier. And of course, in all power converter, we need high efficiency, but we need both high efficiency for large conversion ratio and fine regulation, not just the large conversion ratio only. Regulation is very important and required in most of the systems that we are supporting. We need to meet the thermal constraint with, and high efficiency can help with that. We need fast transient response, reliable and scalable. Scalable is actually one of the most important things, and that ties very directly back to the high power density here. If you have very high power density with a small size unit, we can make it very scalable. And overall, all of that, but still we need to make sure that we have a lower cost. So that essentially when you build power converter, we are talking about essentially these three components here. But the key is how we can use them effectively to implement our converter. Oops, sorry. So in my group here, we are talking about the required techniques and approach to face with this challenge. That we want fundamentally different and smart power architectures. We want new converter topologies and modeling and control to support the new converter topology. We want to make sure that we have the right loss reduction and thermal management techniques. And overall, we want very aggressive miniaturization and integration. So for this miniaturization of the integrated power electronics, we want, oftentimes people talking about increasing the frequency. But with increasing frequency to higher, you can definitely reduce the size of the passive components. So this is going to the desired direction here to reduce the system space. However, we need to add multiple other factors here in order to ultimately reduce the whole system to a certain very low space target. That includes the advanced manufacturing that we are talking about, packaging and device manufacturing. And circuit topologies innovations that in terms of different topologies that we can help reduce the size of the passive components with even the currently available technologies in terms of packaging and device. And system co-design here, that includes how can you co-optimize the power supply with the load, because oftentimes in the design, and this is not part of the talk, but I want to bring this idea, is that the system co-design is between the power supply with the load. So oftentimes we are power supply designer or power converter designer, we are given a certain specification. For example, you need to support this voltage and you need to support this certain transient without knowing much about what the load can actually do. But if we have the co-design between the load application, for example, the processor or any other load, together with the understanding of the limit of the power converter, we can have a system co-design that very efficiently increase the whole system efficiency, not just the power converter efficiency. And an example that you can see very clearly is in Haswell and Broadwell chip from Intel, that they put the converter, the buck converter from 1.8 volt down to 0.9 volt and below onto the Haswell and Broadwell chip. Now, they need to pay a lot of cost in terms of implementing the inductors, and the efficiency of that power converter is not too high in terms of like 98 or 95 kind of range that people often talk about. But the whole system is improved a lot more because that converter now is very last millimeter point of load converter that can actually provide the fast transient response that you can provide the fast DVFS. That is a big factor of the load and the power converter optimization that we can gain in system co-design. And this kind of example should be applied to many other applications, not just in the processor application. So I have been working on this, basically I call the quest for integrated power circuits for all here. When I say for all, is of course we go with different applications. So and my goal is that I hope we'll go to a lot more. So I started with a single inductor multiple output DC converter, and you see through this quest, the whole idea is how to reduce the size of the power converter here. And so with the single inductor, we can support multiple output at the output. That is the size reduction. And this was actually integrated in the a product that was applied in LG phones in 2008. That was their first AMOLED phone that was released. It looks very old now, but that was in 2008. So then moving on, I actually implemented the switch capacitor DC converter. So now we have one single component, a passive component inductor that we can support multiple outputs with larger capability. But what if we can integrate all the passive components inside? That was the switch capacitor fully integrated voltage regulator that I implemented back in Berkeley. That achieved the power density of 1 watt per millimeter square in sub-nanosecond response in terms of, so that's the two-chip, two demonstration there. And then moving on, actually, we applied this into that switch capacitor into a system that we demonstrated that the system and function co-design and co-optimization in the first one core processor over here with the switch capacitor ripple converter. That means we allow the converter to have the ripple of 300 millivolt out of the normal operation voltage of 700 to 800 millivolt. Okay, so you can see that the ripple is really large, but the processor can actually accept that large voltage, and it can function fine. We actually started Linux on that core, and that is the indication of we want to do that system co-optimization to achieve the whole system efficiency, rather than just telling exactly the converter need to provide the steady state output voltage of some level and fix that without understanding of the load capability. And I also have some implantable projects with integrated power converter and RF to DC power converter as well. That's not the focus here. And then we're moving on to what I have been doing from at CU Boulder now is the hybrid converter that we changed the concept of, okay, if we need to step down, we can actually use a hybrid converter that have the inductor as the input instead of the inductor as the output as in buck converter. So that's some architecture here I will show you a little bit later. But the idea here, the key idea here is that now with this inductor at the input, you can actually merge the converter power conversion stage into the environment that it is in. For example, in this case, this inductor can be implemented from the delivery cable, inductance from the delivery cable, instead of using the discrete inductors. And then that was actually also materialized into a integrated converter that's in chip. So this is one chip that my student designed, and actually it was published in ISSCC. If you're familiar with it, this ISSCC is the top most premier conference in integrated circuit design, and using this concept of the cable and the hybrid converter. And moving on, we are actually now actively working on the high voltage large conversion ratio power converter that was actually demonstrated at ECCE 2018 and APEC 2019. And PowerAmerica is actually part of the key sponsor for this direction. So let's talk about the hybrid converter architecture a little bit in order to deal with the challenge of efficient conversion for large conversion ratios, but still we want to maintain the fine voltage regulation with high efficiency. So we want, in that case, we look at this large conversion ratio from 40 to 60 volt at the input and the output of 0.5 to 5 volt here with a very high current density that we need. And the voltage I predict that the voltage actually increase further later on when we actually need to support a larger current at the output. And that's the bottleneck that we saw moving from 12 volt to 48 volt these days. So in order to do that, we want to have multiple stages that block the large voltage conversion ratio from the input here to the output. Now, we have the options of choosing what kind of inductor or capacitor that we put into these stages. So the capacitor, we want them to be there to block the large voltage, and the inductor, we want them to be there to have a soft charge all the capacitors and have a smaller and more integrated, because the capacitor should block most of the voltage that is fed into the inductor. So the option is that how can we put them into these stages? So the first option is that we can put the inductor at the output, right? So and then the capacitor at the input. So this idea is actually very convenient, because when the inductor at the output, great, we can actually use the inductor to control, finally regulate the output voltage, and then the switch capacitor can actually block most of the input voltage here. So another option is that, well, we can put the inductor at the input. Well, first of all, why we change to that? Well, if we have the inductor at the output here, this inductor actually needs to carry all the output current. And we are talking about the very high current density at the output. Well, high current density inductor may not favor that. Well, capacitor doesn't do not like that either, but at least capacitor we can have a chance to have a very low ESR. So another option is that now we move the inductor to the input so that it only needs to check the input current. So smaller input current going through the inductor, that's great. And then the capacitor still block most of the voltage difference between the input and the output. The challenge here is that this capacitor, now you will see a little bit later that this capacitor, when it's switching, is actually connected to the output capacitor. So if you are familiar with switch capacitor converter, that introduce some hard charging loss, and that could be the big disadvantage of this topology. And the last thing is, of course, we can actually combine all of the capacitor inductor at each stage of this conversion. Now, out of all of these options here, we really want to make sure that all the stages need to work together. They shouldn't be the number of stages here. It shouldn't be that this conversion from 40, let's say 48 volt, go to 32 volt here, and then from 32 volt we regulate 32 volt and we go down further and so on. Because if we do that, the efficiency multiplies to the stages, and of course we lose in terms of efficiency. So we want all these stages to work together synchronously and in the most efficient way possible to achieve high efficiency. So this is very quick just to show one example of the inductor of, I call it the inductor first and the capacitor first. So the inductor first here, the inductor at the input, we actually have a demonstration of the what I call the flying inductor hybrid converters. So hybrid architecture, it actually used the inductor here. We actually demonstrated the inductor, getting the inductance from the USB cable. Okay, so no inductor on the die. So this is actually the demonstration that we have here, that the chip we implemented. And then the chip works fine. This is inductor current here, and the whole structure shows that we can actually achieve the efficiency of the, when we are regulating this, the output voltage of 3.6 volt, which is a nominal voltage of the lithium-ion battery. With the cable loss, we achieve a peak of, above 90%. And then without the cable loss, why we remove the cable loss? Because when you are charging the phone, note that nobody cares about the heat dissipation over the cable. One of the reasons why is it has a very large surface area. So if you have additional heat over the cable, it's not big of a deal. But the heat on the phone is the most important part. So that is the key why we are, going after this approach here, because of thermal dissipation reduction in the most important part of the system, that's your phone. So when we calculate that efficiency, we achieve more than 92% efficiency for that 3.6 volt one cell application. But if we go to 2 cell, meaning that 2 cells stacked for the charging for some application like laptops, we can actually achieve the efficiency all the way close to 98%. These numbers are just our very first demonstration. We actually did not optimize all the capacitors that we are using. In the in this year, we actually plan to have a demonstration that we have optimized all and hopefully achieve high efficiency and even higher consideration of all the EMI through the cable. We would address that as well. But look, one thing related to EMI, we actually, this one is the interference for the data transfer of the cable. So this demonstration here is showing that we can actually have the converter that operating in the transient. So the load keeps changing all the time, up and down. And then during that time, we transfer files from the phone to the, from the phone to the computer, and then from the computer back to the phone, and then we play that video on the phone without any problem at all. So simultaneous data communication over the cable together with the power transfer with all the transients necessary. So this was actually presented at ISSCC, demoed at ISSCC, and we received a lot of interest. So now that is the inductor first architecture, and we cover that USB-C application. Now, how about the capacitor first, which is actually the direction that partially supported by PowerAmerica here. We want to implement this large conversion ratio by allowing the switch capacitor to block most of the input voltage, and then the inductor only needs to block a small swing voltage here to finally regulate the output voltage. All right. So now this can be presented in this way, that the switch capacitor still block the input voltage, but then we can have a multiple output inductors here to provide the essentially interleaved currents to the output, or you can say the multi-phase, very similar to multi-phase buck converter to the output. And again, the key here is that all of these stages have to work together synchronously. So this is what I call the family of the converter is multi-inductors hybrid converter, or MIH converter. These inductors will softly charge and discharge the capacitors. And in that way, we can actually support a very large current density at the output, because now the inductors do not need to block the large input voltage anymore, lower input voltage. We can have a lower inductance and higher output current. We can operate this structure in both inductive, quasi-resonant, or resonant modes. But the first focus that we have right now is in the inductive mode. All right, so why we have the whole family? The whole family is because this topology is really agile and flexible. We can actually have a different number of inductors at the output. Okay, So to larger number of inductors target to support a larger current at the output. And then the number of capacitors, voltage levels by the number of capacitors here, we can generate that and we can divide the input voltage to a certain division to feed into these inductors here. So for example, if we use 5 capacitors, we can actually make the input voltage here divided by 6 times. So 48 divided by 6, 8 volts fed into each of these inductors here for the voltage string. And then we can have a different number of capacitors that is managed by one inductor. Okay, so you'll see some examples later through this presentation. And we can have the operation as all these inductors can be operated in just 2 phases, just a normal converter 2 phases, or we can operate these inductors in an interleaving manner. And that can have more inductor charging phases. So that can bring other operation in terms of in the family as well. And again, as I said earlier, it can be inductive, quasi resonant, or resonant operation. We can have a voltage mode regulation, or we have a current mode regulation, because essentially the output here is very similar to the buck converter. So we can inherit all the things that people have been working on and found out all the good things about buck converter. Now we can inherit all of them, but with the benefit that now that buck converter do not need to support the input voltage, but a fraction of input voltage. So what is that topology now in practice? So the first thing we did was in ECCE 2018. That was the work that we worked on in 2017. And this is a dual inductor hybrid converter. So now this dual inductor, because we use 2 inductors, and then you can see that the switch capacitor here is a structure of what we call, very similar to what we call the Dixon star switch capacitor converter. So in this operation, what you'll see later is that the inductor, we have 2 inductors here. So inductor L1 is going to soft charge all the capacitor on the left and soft discharge all the capacitor on the right. And then the inductor L2 will soft charge all the capacitor on the right and soft discharge all the capacitor on the left. So they synchronously working to soft charge and soft discharge the capacitors and bring the charge from the input to the output in the soft charging manner and efficiently. So the first demonstration in ECCE 2018. The operation is this. So let's go into more detail of the operation. So now in the state 1, we have all the high side switches here, or S1 as odd number switches here. So S1, 3, 5, 7, and 9 are on. So when these odd number switches are on, you see that the left side of the left side capacitors are essentially connected to the high voltage node. As here C1 is connected to Vin, and then all the capacitors on the right are connected to ground with their bottom terminal here, or the bottom plate here. At that time, L2 is discharging. So this is the phase, let me see here, sorry. Right, so this is a phase, state 1 or the charging phase A here. So in that time, inductor L2, which is the red color here, is discharging, while inductor L1 is now receiving charge from all these capacitors. So it's charging, the charge goes through this capacitor, go to here, go through the inductor, and the capacitor on the right discharging to the capacitor on the left gets charged, and then also charge the inductor L1 as well. So this inductor L1 is soft charging all the capacitor on the left and soft discharging all the capacitor on the right. Now we go to the next state, which is state 2. In state 2, we keep the switch S9 on to keep freewheeling the current of the inductor L2, but the S8 now is on and all the top switches are off, so the inductor L1 now goes into the freewheeling mode. So that's a freewheeling right here. And then in state 3, we flip the charging state here, that the inductor L2 now is being charged. And then the inductor L1 keeps freewheeling with that switch 8 still on. Now when switch 8 on, you see that all the left capacitors are connected to ground here, for their bottom plate. And then the charge that is received, the charge that C1 received in the previous phase now is discharging to C2. And then the charge that C3 received from C2 in the previous phase now actually discharging to C4. So that's the way that this circuit is working, is that while the charge going from the input keep going through the capacitor, and then also go to the output in a soft charging manner because of the operation of the inductors. So in this case, particular case in state 3, this inductor L2 soft charging the capacitors on the left and soft discharging the capacitor on the right. And then the last state is state 4, that all the inductors go into free-wheeling state again. Now the capacitors here, since all the top switches are off, the capacitors voltages stay the same, stay unchanged. So with that operation, now we have a soft charging and soft discharging for all the capacitors. We implemented this in this converter here with what we call the even level. By the way, the even level here, we call it the even level, slightly different from the way that we call three-level converter. So the three-level converter that many of you would be familiar with is counting the input, the Vin over 2, and then the ground. So that's a three-level. But when we count this converter, we don't count the ground level, and we only count the levels that is generated by the switch capacitor. So if we have 5 capacitors here, for 5 flying capacitors, we actually have a 6th level. So it's consistent with the division, voltage division that we receive at the switching node of the inductors. So now with 6 levels and 5 capacitors, we divide the input voltage by 6 times to feed into the inductor switching nodes. So in this case, in this demonstration at the CCE 2018, we have 2 inductors, 5 capacitors, 6 levels, and only 2 charging phases. So 2 charging phases of inductor L1 and inductor L2, interleaved charging phases. Implemented at 48 volt to 1.8 volt nominal operation, but you can see that essentially the output voltage is just can be regulated by the duty cycle control of the inductor operation of this node. So we can actually provide a large conversion ratio here. We can provide a wide range of conversion ratios here. So the input voltage we demonstrated from 40 to 54 volt, and then the output voltage can be regulated from 1 to 2 volt. We achieve peak efficiency of 95% efficiency with the 2 volt implementation, and close to actually slightly below above 93% efficiency for 48 volt to 1 volt conversion. We use all the GAN switches with the low voltage GAN switches, because these switches now only need to block a smaller fraction of the input voltage rather than large voltages. So we can use a small breakdown voltage GAN. We can use split phase control to avoid residual hard charging. And it was published, and then we actually was featured on GAN Talk Block Medium and Power ParsNet that I guess that many of you are familiar with as well. So now another member of the family is that, well, how about the odd level? So now we use 6 capacitors. So 6 flying capacitor will divide the input voltage by 7 times to feed into the switching node of these inductors. And with that, we actually push ourselves and to do, well, how about we demonstrate all the way to Vin of 120 volt, and then the output voltage of 1.8 volt to 0.9 volt. So with 0.9, you can see that the conversion ratio is 130 to 1. So we demonstrated that, well, okay, so with large conversion ratio, clearly the efficiency dips below 90%, but it's still a very respected number here for efficiency. So we achieve 87.3% for 120 volt to 0.9 volt at 15 amp of load, and then 91.5% efficiency for 120 volt to 1.8 volt at 15 amp of load. The demonstration also, we use the same board and we demonstrated that, okay, how about input voltage 48 volt? So you can see that with 48 volt, 48 to 2 volt, we achieved very close to 95% here. This board was actually my first year PhD student implemented in first semester. So you can see, you can tell that actually it's not super optimized for all of the components here, but even with that, the performance still pretty respectable. So now, as I mentioned earlier, the family can be expanded into operations, different operations. So we can use the same 2 inductor, 5 capacitor, 6 level converter, but now we can interleave the phases more. We can use 6 charging phases, still 2 inductors, but we can make them charge individually each capacitor branch. And why we want to do this? The reason why we want to do this is because if you look into this architecture here, or the operation earlier, we see that whenever we charge and discharge this, we always put the capacitor branches in parallel. And when we do that, we are subjected to some hard charging loss, some residual hard charging loss, if we have some capacitance variation or some other variation. So now, in order to avoid all that variations and still achieve the complete soft charging, we can separate out all the capacitor branches. So the operation is just this. The inductor L1 will soft charge in the first state, only, or in the first charging phase, only soft charge the capacitor C1. So capacitor C1 receives a charge, Q charge here. Now in the next charging state, it will distribute that charge to C2 and charge the inductor L2, and so on. Now C2 receives charge is going to soft discharge that to C3 and inductor L1 and output, of course. And then again C3 to C4 and C4 to C5, C5 to the final output. And after each of these charging state, we have the freewheeling state for all the inductors. So that makes the interleaving operation that you see on the right here. So in each cycle or fundamental cycle of the converter operation, we have the 3 times that each inductor is being charged and discharged, okay? And then, but for the capacitors, in one operating, fundamental operating cycle, we have only 1 time that a capacitor is charged and discharged. So this converter can completely remove all the hard charging due to variations of the capacitors or variations of the aging in the capacitors and so on. The caveat is now we actually need to have the low side switch need to switch faster frequency, and then the high side switch, now every time you are charging this, it actually, the whole output current is flowing through the high side switches. So that's something that we need to pay, no free lunch. So the efficiency here goes down to 92.1% efficiency for 48 volt to 1.8 volt at 4 amp first demonstration. But note that, again, we now are free from the variations in terms of capacitance and voltages or transient, and we still achieve soft charging all the time. So how about a different number of capacitors that each inductor manages? So this is the APEC paper that we presented actually a few weeks ago, a couple of weeks ago. So now one inductor is not managing 3 or 4 capacitors anymore. It actually manages 2 capacitors. So 3 inductors now managing 5 capacitors in total. And why there's a 5? Because the last capacitor, when it is discharging, is actually discharging straight to one of the inductors. So that's why we have this only 5 capacitors, but 6 levels still. So that 6 levels make it divide equally to all these inductors. So now you can, from the operations, you can see that, well, that's the way that the circuit works now. It's actually receiving charge into C1, and then soft charging C1 by the inductor L1, and also at the same time C3 delivers charge to C4. And so in the next phase, now C4 is expected to deliver the charge to the lower capacitor C5, and C1 deliver the charge to C2 by the operation of soft charging from L2. And then in the last charging phase, we have that inductor L3 is soft charging or soft discharging the capacitor C5, soft charging the capacitor C3 by getting charge from the capacitor C2. So, and then in the middle of all these phases, of course, we have the freewheeling states for all the inductors. Now note that all these inductors need to see the swing at the switching node here only by Vin divided by 6. So this one, now with the 3 inductors, we increase the output current to very high, and we achieve 40 amps at the output, and 80 watt with 95% efficiency peak at 40 volt, regulate down to 1 to 2 volt output voltages. So now we move this further. Well, why not 1 inductor, 1 capacitor? So this is actually very similar to what some people here are familiar with, the topology called the series buck converter. So we come from a different angle. We come in with a hybrid converter with a very good background in switch capacitor circuits, and then we kind of, meet the other group going from the inductor side. Actually, this is the group from Japan, Nijishima's group. Came up with this topology, I think, quite a long time ago in 2006. We independently, just come to merge with this direction here. So it's very similar to the switch series capacitor buck converter. So we use 4 inductors, 3 capacitors, 4 levels. And now, but what we see here is, what is interesting here is that we can operate this converter in any number of phases we want, from the 2 charging phases or 4 charging phases, or even some different versions of this that we have not demonstrated. But the key idea here is that now each inductor only needs to charge and discharge 1 capacitor branch. So now with this topology, we are not afraid of any capacitance variation, and we always achieve the complete soft charging all the time. And we have a number of inductors at the output 4 now. So that means we can support a peak current of 100 amp at the output, which is one of the milestones that we promised we deliver for PowerAmerica project at the end of March, actually. So with 100 amp at the output here, peak current, this converter actually achieved 100 watt at 1 volt, okay? But we also demonstrated that, well, how about 5 volt? Yeah, we can regulate all of this output voltages. So with 5 volt, we are talking about 500 watt for 1 converter unit. We achieved the efficiency of 92% at 1 volt, peak efficiency, 93.5% at 1.6 volt, which is around the number that, like Haswell and Broadwell chip would like to use for their server application. And for 2 volt, we go up to very close to 95% efficiency. And with 5 volt, excuse me? Oh, sorry. So with 5 volt, we can actually have the whole power density of 2,200 watt per cubic inch in implementation.
We're sorry, your entry is not valid, or the meeting has not started yet. Please re-enter your access code or meeting number followed by the pound sign.
Just please ignore that.
Oh, okay. All right. So then we have a soft charging. So all the waveforms on the right just show that the converter indeed works, and all of this data are reliable. Okay, so I'm almost done here. So
we're sorry,
what's next?
Your entry is not valid, or the meeting has not started yet. Please re-enter your access code or meeting number followed by the pound sign.
So what's next in terms of research here? So I believe that more advanced hybrid converter topologies will come. Not just this family that we have shown that you can do a lot of things with this family, but more hybrid converter topologies will come because there's need for it. They will cover larger conversion ratio even. They can support impossibly high or large current density that right now we think is impossible. Multiple stages, but all of these stages have to work together synchronously for efficiency. Inductor and capacitor will be integrated in one way or another, and capacitors, we already know the Murata can actually integrate this very well. Power switches, GaN devices, more advanced modes will be more integrated, and actually EPC show one of the recent development at APEC that I believe many of you attended. Why we want to do all this? Because the whole converter will be integrated. As everything has been, our power conversion has been slowed. We need to speed up, and I believe we'll get there. And this applies not just to the converter for mobile phones I show as example here, but it should apply to all the GAN application with very high voltage that I just showed you earlier as well. So my PhD students, I'd like to thank them for the PhD students 3 now, and I expect to increase to at least 2 more in this year. And thank you very much for your attention, and I expect any questions you have.
Thank you very much, Dr. Lay. That was a very information-rich, very informative presentation. I really appreciate your time and preparation. We have time for questions, so please, again, pull down the chat window from the top of your WebEx bar and type in your questions, and I'll be happy to read them aloud so that Dr. Lay can answer your questions. Okay, I don't see any questions coming through yet, so let's just give it another minute.
Actually, in this tool, do we have something like raise hands?
Yeah, but this works better, I think. Okay, here's the first question. Okay. What is the required switching frequency of the lower FET?
Yes, so for the lower FET here, now it depends on the converter that we're talking about. So if we are talking about the last converter here, it's actually at the same frequency with all the high side switches. So right now we operate most of these converters at around a few hundred kilohertz. So from 150 to 400 kilohertz. The reason why we operated relatively low switching frequency because of the limit in the GAN drivers and GAN switches that we have right now. But as far as we heard from EPC and then the drivers from TI and even EPC switches that they have the integrated drivers, they can reach up to tens of megahertz now, and that's our target to go next, so that we can reduce all of these component sizes. But related to this particular converter that has only a different operation here, so in this converter, because the low side switches need to switch at a 3 times faster switching frequency, as you can see here, in terms of discharging the inductors. So the top switches are switched at 150 kilohertz, and the bottom switches are switched at 450 kilohertz.
Okay, thanks. The next question is, what is the impact of self-heating at the switching frequencies you are using? And at what frequency will it cause self-heating that deteriorates performance?
That's a great question. So I can tell you that I've been on topologies for a long time. I can't claim that I'm very experienced in GAN switches. So we have been using them as the customer more than the researcher. So we did not do this thorough research on the self-heating mechanism of the device, of the EPC device that we use. So I don't have the good answer to your question. But I look forward to someone who asks a question with experience, could educate us how to actually do this.
Okay, are there any more questions or comments from anyone else on in the meeting?
Comments are certainly welcome as well.
Okay, I've unmuted everyone, so if there are any last-minute comments before we wrap up, please feel free. Okay, if there are no further comments, then I'd like to thank Dr. Lay again. I really appreciate your time and preparation. And thank you all for joining us again. And we'll see you next month on Wednesday, May 1st.
Thank you. Thank you, Rogelio, and thank you, everyone, for attention.
You're welcome. Have a great day.
Thank you. Goodbye.
Bye-bye.
Mm-hmm.